Today we are going to do the chapter 24. Last time we went through it, and I hope you get some understanding. We repeat it again. It's called electromagnetic wave. Electromagnetic waves. So. In short, it's called EM wave. EM wave. How does EM wave form? That's how we're going to discuss it. How does it get in there? Because you have to understand the electromagnetic wave, because all the things you see is basically electromagnetic wave. The light come out here, the sunlight, the radio wave, Rush Limbaugh's radio wave, and then the TV signal, again, is the EM wave. And infrared, again, is EM wave. And on, all the stuff you're talking about is EM wave. So the transmission of internet is EM wave. So that's why this part of it is very important. Now, we have to thanks to one particular person doing this contribution, actually two. One is Maxwell. Maxwell has the idea on paper. Another one is Hertz. Hertz is the person doing the experiment to prove the Maxwell theory. Initially, and then later on, a lot of people to do it. So one thing he is talking about is on the section 24.1. This 24.1 is talking about one particular section, in which case is talking about the Ampere's law. And then more useful one is called the generalized one. The Ampere's law in the particular cases is integral of B dot ds. The line integral of magnetic field around a closed path is equal to mu sub 0 I. So basically, what this does is there's a current go through in here, and the integral the closed path in here. In these cases, this is I going out, and then the magnetic field go this way. That is the relationship. And in these cases, important is that has a current go through. But in the current go through, a lot of times, there's a lot of other elements other than the resistance. In one extra element may be come across capacitors. Because when you go through different medium, the different medium forms a capacitor function. So Maxwell is trying to solve that dilemma. How we can solve this extra term, they call. So he considered this is a cone, in which cases when you go through the space, they have an imaginary capacitor there. So if they have a capacitor going through, then you got to including another additional term. This additional term of the current is called I sub D. It says you have to take this term into account. In which case it's called displacement current. Displacement current. So that is equal to epsilon sub 0 d phi sub e dt. So what means is the change, time rate change, including this term, in which cases is time rate change of electrical flux, change of electric flux. Then time rate change of electrical flux will produce current. Now what they give him this idea, in their cases, he has the term, because he got get the terminology from Faraday's law. He get the inspiration from Faraday's law. What Faraday's law is a change of magnetic flux will produce EMF. That means the Faraday's law. Faraday's law saying that integral or electrical field dot ds is equal to time rate change of magnetic flux. So he got the inspiration from this, and he says something like that. So with this assumption he created a generalized Ampere's law. That means including I sub d in here. Including I sub d. Including I sub d in here. So that is what generalized Ampere's law. This turned out to be the generalized Ampere's law. So writing the generalized Ampere's law properly, then we get this. Integral of phi dot ds, we have equal to mu sub 0 I plus mu sub 0 ipsilon sub 0 d phi sub e dt. So here is the generalized Ampere's law. After that is done, then Maxwell say, okay, now we summarize all the electricity and magnetism are fused together. And that build up what we call the Maxwell equation. So we come through on the section 24.2 is creating, grouping together. 24.2 is called Maxwell equation. A lot of PhD people in physics, in WE, a lot of different fields. Their job is try to solve the Maxwell equation. In which case, the Maxwell equation is grouped in four. Okay, the four turn out to be one is integral of E dot dA. This one is equal to Q divided by epsilon sub 0. And this one is called Gauss' law. And then integral of B dot dA, in that case, is equal to 0. That is called Gauss' law in magnetic field. And then the Gauss' law, and then the next one is a Faraday's law, dot ds, equal to minus dVb dt. This one is called Faraday's law. And the next one is in here is P dot Ts, the generalized MPS law, in which case we go to mu sub 0 I plus mu sub 0 epsilon sub 0 dv sub E dt. So this is a generalized Faraday's generalized MPS law.
What was the second law called?
The second law is the Gauss law related with magnetic field.
Thank you.
So with this grouped together, they try to use it and try to getting some idea. The major idea in here is somebody gives Maxwell a inspiration, means the electrical field, the changing of magnetic field will induce electrical field. The time rate change of electrical field will introduce electrical field. Variation of electrical field will induce magnetic field. And variation of magnetic field will introduce the electrical field. That means if a B change, then will give us electrical field. And electrical field change will give us magnetic field. That means, and vice versa. And he getting this idea, then another idea is electrical field and magnetic field is coexistent when it is in traveling in space. So this is the idea of section 24.3. Here they try to develop the EM wave, the EM wave. Now we try to do the EM wave from first equation, electrical field, in which case is the Faraday's law. Faraday's law says integral, the line integral on E dot ds, is equal to minus dBV dt. So the Faraday's law very spell out exactly. Change of the magnetic field will induce the electrical field. This is Faraday's law. Then from the Ampere's law, generalized Ampere's law, please take a good look at it. Now, if the electrical conductor is not around, no electrical conductor, it's a free space, then in that case the current is equal to 0. So using this, then you have integral of magnetic field, line integral of magnetic field is going to be equal to mu sub 0, epsilon sub 0, dv sub E dt. So this is Ampere's law, generalized Ampere's law. So just observing this two law, then it gives you certain